It is New Year's Day, 1995. The location is the Draupner oil platform, a massive structure anchored in the churning, freezing waters of the North Sea. The crew is accustomed to rough weather. This is the North Sea in winter, after all. But at 3:20 p.m., the onboard instruments register something that, according to the physics of the time, should not exist. Amidst a sea of 12-meter swells, already significant by any standard, a single terrifying wall of water rises up. It towers 25.6 meters, or 84 feet, into the air. It slams into the platform with a force that defies calculation. This was the Draupner wave. And it was the moment the world of science finally had to admit that the old ghost stories were true. For millennia, sailors had returned to port with trembling voices, whispering of holes in the ocean and monsters of liquid glass that appeared under clear blue skies to snap supertankers in half, like dry twigs. For just as long, scientists dismissed them. They called them tall tales, the drunken exaggerations of weary mariners. The mathematical models of the 20th century, which relied on the orderly bell curve predictions of the Gaussian distribution, insisted that such waves were statistical impossibilities. A 30-meter wave was supposed to happen once every 10,000 years. But the Draupner wave proved that the ocean was not a predictable, orderly system. It was chaotic, non-linear, and occasionally murderous. For the 30 years following that event, humanity struggled to predict these monsters. We built stronger ships and drilled deeper for data, but the questions of when and where a rogue wave would strike remained a terrifying roll of the dice. That is, until now. Welcome to a deep dive into the Neptune Algorithm. This is the story of how a team of researchers from the University of Copenhagen and the University of Victoria used a new kind of artificial intelligence to finally crack the code of the ocean's deadliest phenomenon. We are going to explore how they turned the chaotic fury of the sea into a solvable equation, and what this means for the future of maritime travel. To understand how they did it, we first have to understand the scale of the problem. To teach a computer how to spot a monster, you first have to show it where the monsters live. The foundation of this breakthrough, led by researchers Dion Hafner and Johannes Gemrich, lies not in a single eureka moment, but in a mountain of data that would drown a human analyst. The data came from a vast network of ocean eyes. For decades, highly advanced buoys and cabled observatories, including the pioneering Neptune Observatory off the coast of the Pacific Northwest, have been silently recording the heartbeat of the ocean. These sensors measure wave height, crest length, and trough depth 24 hours a day, 365 days a year. The research team compiled a dataset of staggering proportions. They took records from 158 buoys scattered across the globe, continuously recording for years. When stitched together, this dataset represented an equivalent of 700 years of continuous ocean observation. Inside this digital ocean, they identified over 100,000 rogue waves. These are defined as anomalies that are at least twice the significant wave height of the surrounding sea state. The sheer volume of this data revealed a chilling truth immediately. The once in 10,000 years theory was dead wrong. Rogue waves were happening every single day, somewhere in the vast, unmonitored expanses of the world's oceans. The beast was not rare, it was just elusive. But having the data is one thing. Understanding it is another. This is where the story takes a turn into the cutting edge of computer science. The brilliance of the Neptune algorithm lies in the type of artificial intelligence that researchers chose to use. In the past decade, you have heard a lot about deep learning. Deep learning models are powerful, but they are often called black boxes. You feed them data, and they spit out a prediction, but they cannot tell you how they arrived at that answer. For a ship captain staring at a radar screen, trust me, I am an AI, is not a comforting explanation when deciding whether to alter course by 500 miles and burn tons of extra fuel. The researchers instead chose a method called symbolic regression. This is fascinating because it functions differently from your standard neural network. Imagine a master mathematician who does not just memorize the answers to a test, but derives the formulas from scratch. Symbolic regression analyzes the data and tries to build a mathematical equation that fits the patterns. It tests millions of combinations of variables, wave height, steepness, water depth, spectral bandwidth, until it finds the simplest, most elegant formula that explains the phenomenon. The result is what we call a glass box AI. It does not just output a probability, it outputs an equation. It tells the scientists why a rogue wave is forming. This transparency led to a shock in the oceanographic community. For years, the prevailing theory was that rogue waves were born from something called modulation instability, also known as the Benjamin-Fehr instability. This is a complex nonlinear mechanism where waves essentially steal energy from their neighbors to grow vertically. It is a very exotic, complex physics explanation. However, the Neptune algorithm's equation said otherwise. It revealed that the primary culprit for most rogue waves was actually something much simpler: linear superposition. This is a concept known since the 1700s, but it was often overlooked in the hunt for more complex explanations. Linear superposition is essentially a traffic accident at sea. It happens when two or more different wave systems cross paths. Picture a fast-moving swell generated by a distant storm off the coast of Japan. Now, picture a slower, local wind-driven chop generated by a low-pressure system nearby. These two systems have different speeds and directions. Linear superposition occurs when they cross paths at the exact wrong moment. Their crests stack on top of each other, and for a brief, violent window of time, they combine to form a wall of water. The AI showed that this bad luck alignment was actually predictable. By monitoring the spectral bandwidth, which is the range of frequencies in the waves, and the directionality, the algorithm could calculate exactly when these systems would intersect to create a monster. So let us bring this down to the water level. How does this translate to safety at sea? Let's visualize a modern container ship, let's call it the MSC Goliath, steaming across the North Pacific. In the ship's bridge, the captain is monitoring a new display integrated into the electronic chart display and information system. This is the operational face of the Neptune technology. Instead of just showing current weather, the system is pulling real-time data from the global buoy network and satellite altimetry readings. It processes this data through the symbolic regression equation derived by the AI. It is 12 p.m. The sea state looks rough, but manageable. The significant wave height is 6 meters, standard procedure. But then, at 12:05 p.m., the algorithm detects a shift in the spectral energy. That long period swell we mentioned is about to intersect with the local waves. At 12:06 p.m., the system flags a red zone on the captain's chart, a 50 square mile patch of ocean 10 miles ahead. The probability of a rogue wave event in that sector spikes from 0.01% to 85%. At 12:10 p.m., the captain alters course 5 degrees to starboard. It is a minor adjustment barely felt by the crew. But at 12:45 p.m., a buoy in that red zone records a 22-meter wave, a wall of water that would have smashed the Goliath's bridge windows and swept containers overboard. The ship, safely 5 miles away, feels only a heavy roll. This is not science fiction. The University of Maryland, building on similar principles, has developed neural networks capable of predicting rogue waves 1 to 5 minutes in advance, using direct buoy data. While 5 minutes sounds short to us, in the world of maritime operations, it is an eternity. It is enough time to batten down hatches, secure loose crew on deck, and most importantly, turn the ship's bow into the wave to ride it out safely, rather than taking it broadside, which is often fatal. The implications of this technology extend far beyond just saving lives, though that is its noblest purpose. The economic ripples are massive. The global shipping industry moves 90% of the world's trade. Every year, hundreds of millions of dollars are lost to heavy weather damage. Containers are lost overboard, an average of 1,500 per year, with catastrophic years seeing far more. Ships suffer structural fatigue, and insurance premiums skyrocket. With reliable rogue wave prediction, we are looking at a paradigm shift. First, there is route optimization. Ships can take more direct routes, avoiding only the specific pockets of danger rather than skirting entire oceans due to vague storm warnings. This saves fuel and reduces carbon emissions. Second, consider insurance and liability. Marine insurance companies are already eyeing this tech. Ships equipped with Neptune-certified AI systems could see lower premiums, incentivizing the entire fleet to upgrade. Then there is the offshore energy sector. Oil rigs and wind farms are sitting ducks, they cannot move. However, knowing a rogue wave is coming minutes in advance allows for emergency shutdowns. They can stop delicate operations, lock cranes, and move personnel to safe zones. This could prevent disasters like the 1982 Ocean Ranger tragedy, where a rogue wave sank a mobile offshore drilling unit. Looking to the future horizon, the Neptune algorithm is just the beginning. The next phase involves integrating this AI with the next generation of autonomous ships. Rolls-Royce and other maritime giants are already designing ghost ships, massive cargo vessels with no crew, piloted entirely by AI. For these vessels, a rogue wave is the ultimate boss fight. Without a human captain to feel the sea, the ship relies entirely on sensors. A rogue wave prediction algorithm is the sensory cortex these ships need to survive. Furthermore, we must consider the changing climate. Climate change is heating up the oceans, adding more energy to the system. Recent studies suggest that extreme wave heights are increasing in the Southern Ocean and North Atlantic. The 100-year wave might soon become the 10-year wave. As the ocean becomes more hostile, our reliance on AI to navigate it will shift from a luxury to a necessity. We will never truly conquer the ocean. It is too vast, too powerful, and too wild. But the Neptune algorithm represents a fundamental shift in our relationship with it. We are moving from an era of superstition and fear to one of understanding and anticipation. For the sailor looking out at the black horizon, the sea is no longer a chaotic roulette wheel. The monsters are still there, prowling the deep. But for the first time in history, we can see them coming. And that makes all the difference.